In this video, we're looking at ideas in section 5.7 concerning enthalpies of formation. Our goal is to be able to identify and use what are called standard enthalpy of formation reactions. So two different skills. Can we identify a standard enthalpy of formation reaction? And how will we use that information to calculate enthalpies of other reactions? Let's start with the identify part. So I'm directing us to information within the e-text. Points out that enthalpy values are tabulated in many different ways. You can look them up. Maybe they're in terms of the enthalpy corresponding to vaporization when you go from a liquid to a gas, enthalpies of fusion, which would be the energy to melt a solid, enthalpies of combustion, describing combustion reactions. A lot of different ways that you can have it tabulated. Here I show different combustion reactions. Methane, hydrogen, glucose, butane all can be involved in combustion reactions. And here you see the corresponding enthalpy change. So a lot of different ways that enthalpy values can be tabulated. I agree with the authors when they say a particularly important one is when you tabulate the formation of a compound from its constituent elements. This is when it's describing the enthalpy of formation. So we'll see that symbol oftentimes, delta H sub F, corresponding to an enthalpy of formation. So when it says a compound coming from its constituent elements, let's say you're looking and you want to compare different iron oxides. So here's several different formulas for different kinds of iron oxides, different oxidation numbers for the iron in each case. And in each example, when it says coming from its constituent elements, these are all combining iron and oxygen in different proportions. These are all different reactions that would have different enthalpies of formation. They're coming from their constituent elements, and these would be things that would be tabulated that we'd be able to look up and find the corresponding enthalpy change. So the description here, the standard enthalpy of formation, we're going to start with the elements, make a compound. The elements are in their standard state. The standard state portion means, and that's what this superscript 0 means, it's finding the elements in their everyday conditions in terms of pressure and temperature. When you have a reaction like that, the enthalpy change for the reaction is the standard enthalpy of formation. That's what that symbolism means. So this idea that they're usually reported at room temperature, about 298 K, we have to say, well, what are the elements then in their standard conditions? Here's an example, and it's pointing out that the standard condition for hydrogen, if you need that as an element, it's going to be hydrogen gas. O2 would be the way to get oxygen atoms. For carbon, carbon has different forms that you might be familiar with. Diamond would be an example. Turns out that the elemental form that we use in these, the most stable is carbon as graphite. So how do we write and make sense of these kind of equations? I'm going to go to a portion within the e-text here. I think this sample exercise does a good job of describing it. Let's see what the authors say.
For which of these reactions at 25 degrees Celsius does the enthalpy change represent a standard enthalpy of formation? For each that does not, what changes are needed to make it an equation whose delta H is an enthalpy of formation? The standard enthalpy of formation is represented by a reaction in which each reactant is an element in its standard state and the product is 1 mole of the compound. The standard enthalpy of formation is represented by a reaction in which each reactant is an element in its standard state and the product is 1 mole of the compound. We need to examine each equation to determine 1. Whether the reaction is one in which 1 mole of a substance is formed from the elements, and 2. Whether the reactant elements are in their standard states. Let's start with A. In A, 1 mole of Na2O is formed from the elements sodium and oxygen in their proper states, solid sodium and O2 gas respectively. Therefore, the enthalpy change for reaction A corresponds to a standard enthalpy of formation. Note that when we balance chemical equations, we generally use whole number coefficients. But when we write an expression for an enthalpy of formation, we must have one product with a coefficient of 1. This sometimes leads to a fractional coefficient for one or more reactants. In B, potassium is given as a liquid. It must be changed to the solid form, its standard state at room temperature. Furthermore, 2 moles of KCl are formed, so the enthalpy change for the reaction as written is twice the standard enthalpy of formation of KCl. This means that B is not an equation associated with an enthalpy of formation. The equation for the formation of 1 mole of KCl is 1 mole of potassium solid plus a half a mole of chlorine gas, giving 1 mole of KCl solid. Reaction C does not form a substance from its elements. Instead, a substance decomposes to its elements. So this reaction must be reversed. Next, the element carbon is given as diamond, whereas graphite is the standard state of carbon at room temperature and 1 atmosphere of pressure. The equation that correctly represents the enthalpy of formation of glucose from its elements is 6 carbon graphite plus 6 H2 gas plus 3 O2 gas, giving 1 mole of C6H12O6 solid. The standard enthalpy of formation of a compound is the change in enthalpy for the reaction that forms 1 mole of the compound from its elements with all substances in their standard states. This happens in part A for this sample exercise.
So I think he gave a really good overview of this particular question, how we would go about solving it, and what makes something a standard enthalpy of formation reaction. So if I were to summarize a few features there, what kind of problem solving? Well, let's look at the product. We're going to see 1 mole of a single compound being formed. That was the example when we had 1 mole of sodium oxide being formed. When I look at the reactants, we've learned that fractional coefficients are possible. In fact, they're likely. If I'm forming 1 mole of the product, it might mean that I have fractional coefficients for the reactants. When I look at those reactants, I'm going to be looking for elements in their standard state. So if I need oxygen or hydrogen, I'm going to be using diatomic molecules. Metals like sodium, iron, mercury will be all by themselves. One thing to be careful of, mercury in its standard state is a liquid. It's one of the few liquids that we have on the periodic table under standard conditions. We've seen that the description for carbon would be carbon in its graphite form. One other novel one to bring to your attention for sulfur, it's an S8 molecule. Another thing, if we have these skills, we have to be careful and understand how the questions can be asked. I find that the questions can be asked in different ways. Look back to the wording for this one. For which of these reactions at 25 degrees C does the enthalpy change represent a standard enthalpy of formation? So it would clue me in these words, standard enthalpy of formation. I'm going to be identifying the reaction that has that description. Here's another one. Same topic, but it's asked a little bit differently. This is from the e-text. If the heat of formation of delta H liquid is negative 286 kilojoules per mole, which of the following thermochemical equations for the formation of H2O is correct? This is asking the same thing. Anytime you see the word formation, heat of formation, it's going to be asking about the standard enthalpy of formation. So take a second, see if you can answer that one. A, B, C, D, E. Which of these do you think is correctly identifying the standard enthalpy of formation for H2O liquid? Here's another example. This is from Mastering Chemistry. It's asking about the same skill, but the wording is again a little bit different. For which of the following reactions is the value of delta H for the reaction equal to delta H sub F for the product? This is another way that I'd be looking for a question about the standard enthalpy of formation. That's the symbolism for it, the delta H sub F, the enthalpy change for the standard enthalpy of formation. I don't think they're trying to be sneaky in that part. There's just different ways that different conventions, different ways that you might see the question posed. So take a second, see if you can answer this mastering question. A, B, C, D, E. Which of these would be a standard enthalpy of formation reaction? So I've introduced the idea of how do we identify a standard enthalpy of formation reaction. It might be given the symbolism or the phrase. Why is this useful or helpful for us? Let's see how we now use these enthalpies of formation to calculate the enthalpies for various reactions. So I'm going to go back to the e-text here. It points out that the standard enthalpy of formation, like any other enthalpy values, Hess's law is applicable. So it's using an example of saying, let's say this is the combustion reaction we're interested in. They looked up different standard enthalpy of formation reactions, and that's what's being expressed down here. In some cases, they've had to reverse the reaction, or they've had to adjust the coefficients. But they point out that using Hess's law, you can get a delta H for the reaction that's in terms of all of these standard enthalpy of formation. Their point is, Hess's law, yeah, it works with standard enthalpy of formation. What else is there to it? Notice how it takes those, and when it groups it, it says you can reduce that and only think about it now in terms of these different standard enthalpy of formation reactions. You don't have to go through the effort of seeing how it works with Hess's law. Evidently, you can just look to the different standard enthalpy of formation reactions and use that data in order to come up with the answer. I like this pictorial representation for what they're showing going on. They're pointing out that you could go from the reactants to the products in this combustion reaction. Or you could think about it this way. Let's say you took the reactants and you took them apart to their constituent elements. Then you took those elements and you brought them together to make the products. Enthalpy being a state function, that'll work. You can either go from the reactants to the products, or you consider the energy that it takes to take them apart to their elements and the constituent elements, and then put them back together. You don't have to physically have this take place, but Hess's law says it doesn't physically have to take place. You can still do the math as long as you're considering final minus initial. So that's where the authors point out that we can do this for any reaction as long as we have the standard enthalpy of formation data. We can come up with a delta H for the reaction if we consider what does it mean to consider the enthalpy of formation for the products and the reactants. Our setup is going to be the products minus the reactants. That's similar to thinking about the final minus the initial state. And this is saying that we're going to add up the mole amounts for all of the coefficients for the products minus for the reactants. Because the reactants, after all, are the ones that we are taking apart. And the products are what we are forming. Let me show you an example. So here's a question. Using standard enthalpies of formation, let's calculate the enthalpy change for the combustion of methane. So here's a balanced equation for the combustion of methane. I would look up tabulated values for the different standard enthalpies of formation. And then I'm going to use my expression here to add up the contribution from all of the products minus all of the reactants, where these leading terms are the stoichiometric coefficients in the balanced equation. So products minus reactants, I see 1 mole of CO2, and I have a enthalpy value for that. I have 2 moles of H2O liquid. I've got an enthalpy value of that. When I write this down, I usually put it in brackets to remind myself I'm going to take that entire term, that's the products, minus the term for the reactants. And I put the reactants in these brackets as well. That helps me keep track of the sign. Now you notice I have a value for CH4. Why do I not have a value for the O2? That's oxygen in its elemental form. If something is in its elemental form, its value is going to be 0 for the standard enthalpy of formation. So anything in its elemental form, don't expect to find it in the table. This is why it's really helpful to be able to have tabulated standard enthalpy of formation reactions, because this is a very easy calculation for us to do. Here's some suggested problems for you to think about. These first two are different ones where you're being asked to write the standard enthalpy of formation reaction. And then 5.73, 5.74, you're directed to the appendix to look up those standard enthalpy of formation values and do an analysis where you're going to be grouping products minus reactants to get the overall enthalpy change for the reaction.